And Deniz, you can get started. Thanks.
Thanks, Sam, for the introduction. So I'll talk today about just convergence properties of some optimized adaptive importance samplers. This is actually like the class of algorithms I'll describe. They're actually not like very novel, but some of the analysis I'm going to present is hopefully going to be novel. So yeah, so very briefly, I'll just give some background on adaptive importance sampling, and then I'll derive these convergence rates and the error rates of algorithms that adapt their proposals in several, like in two different cases mainly. Mainly it's exponential family proposals, and if time permits, I'm going to describe what happens with more general proposal distributions, and there's going to be like a small short discussion. So we just are interested in estimating this form of integrals. It's like a very generic problem. In my notation here, phi is a test function and pi is our target, which we want to estimate or sample from, let's say. Here, what we want to do is we would just want to compute this integral with respect to pi. And here pi is denoted, we have this unnormalized big pi, and then we denote the normalizing constant as z, right? So we, in a typical scenario, we can just evaluate the unnormalized distribution big pi here, and we want to compute this integral. So the standard way to do this is, of course, I'm not gonna, because I only have 25 minutes, I'm not gonna introduce the importance sampling, but what I'm gonna just describe this scheme. One way to do this estimation of this integral is just perform self-normalized importance sampling. And as many of you probably know very well, is the procedure goes as follows. You just choose a proposal distribution. In this case, because of the rest of the talk, mainly I parameterize the proposal, but you just choose a proposal measure. You sample from this proposal. So these samples are coming from the proposal and not from pi, obviously. What is done in self-normalized importance sampling is you compute weights to account for this discrepancy. And the estimators for the importance samplers are constructed this way. So it's a weighted combination of your samples evaluated at your test function, right? So these weights are coming from this unnormalized Radon-Nikodym derivative. You have the ratio of pi over q theta. And then these weights are normalized, right? This is like a one slide description of importance sampling, because I'm sure many of you just know what it is. So we want to basically, we are interested in this sort of estimators of the integral, and we want to evaluate, I want to discuss today the error properties of this sort of estimators under the scenario that we adapt our proposals over iterations. So we know that these classic estimators, they converge in LP with square root of 1 over square root of n rate, right? More precisely, what I'm going to use over like this talk is this error rate. This is the MSE bound for the estimator I described. So this is the estimator, this is the self-normalized importance sampling estimator, and this is the quantity we want to estimate. And this is the MSE, expected error, squared error. This error, actually, it's very well known that we have the 1 over n convergence rate in terms of number of particles. Here, n is the number of samples you use to build your Monte Carlo estimator. This particular error bound, it was, at least to my knowledge, I first saw in this paper. I'm sure like this is a very old, of course, derivation. So this error bound is structured as follows. We have one constant that's basically related to the supremum norm of test function. So one thing we do here is that we assume test functions are bounded. Let's say it's an indicator function or anything that is bounded. And then we have n, that is the number of particles. So we know that the rate is 1 over n. And then we have this quantity that we call rho here. And rho is basically described this way. So it is the ratio, square ratio of pi and q, your proposal and the target, and integrated against q, right? So there's one intuitive explanation or intuitive understanding of this quantity is it's basically the chi-square divergence plus 1. So if you go back and look at the MSE bound, an intuitive picture says, okay, the error is actually quantified by how far away you are from the target. That's chi-square divergence plus 1, right? So this is intuitive in some sense, because if you choose a proposal to perform importance sampling, it makes sense to choose a proposal that's close to your target in some way. And this MSE bound shows actually this metric should be the chi-square divergence, or at least the MSE is quantified by this quantity. Okay, so we know that by the MSE bound, if you just build your self-normalizing importance sampler, it's clear that if your proposal is far away from the target, the error will be big, right? In order to tackle this problem, what people have done is that people develop these adaptive importance samplers. So what adaptive means here is that you don't just choose a proposal and do importance sampling. You actually build iterative schemes to evolve your proposals in some way that helps the estimation procedure. And you do this iterative evolution of samplers, proposals, and then you basically do the importance sampling again and again, right? So very popular way to do this has been population-based adaptive importance samplers, which is not the, we are not going to consider them in this talk. What people used to do is people just have like a weighted mixture of Gaussians, and they evolve these Gaussians doing resampling, and then again, sampling from these proposals and so on. So what we are going to consider here is we are going to consider a simpler case, which I call parametric adaptive importance sampler, which is quite intuitive. So you just parameterize your proposal. So you choose a family of proposals, and you parameterize it with theta. So that's depends on your family. And instead of updating a mixture of Gaussians and so on, you just update your parameter, right? So that's going to be your update of the basically your proposal. And you somehow want to improve your proposal over time. So obviously the question then emerges that what should you actually do, right? So should you minimize KL divergence? Should you minimize the variance of the weight function, which is actually the chi-square divergence, or should you minimize another quantity? That's going to be the question later, and probably you're already guessing what should be done. So I'm just going to consider the parametric adaptive importance sampler. So I'm just going to describe this generic adaptive importance sampler before I move on to some results. So the algorithm we consider here is just as I described, can be described like very simply, that you have an adaptation step that you update your parameter, and you do the importance sampling with that parameter theta t, right? So that's just the scheme. So that's nothing different than what I showed before, except we update the parameter over time. So if we adapt the result that I showed earlier, so that's the same result, just adapted with theta t's now. You can see that this estimator that evolves now over time, because as we update our theta, we build different estimators. You can see that the error bound will, of course, also evolve over time, right? So this is going to be rho theta t instead of rho theta, and the rest is defined in the same way. And this obviously suggests us, well, first of all, tells us something about the adaptation scheme. So any adaptation scheme that does something over time should actually minimize rho. If they minimize rho, then they are good adaptation schemes. If they don't explicitly minimize rho, then we possibly don't know in theory what happens. For example, for the case of KL divergence, which is done in the literature to adapt the proposals, they converge empirically, but actually when it comes to proving something about it, it's not enough, because KL divergence does not upper bound this quantity, right? Which is, I said, the chi-square divergence and also the variance of the importance weights. So it has a lot of intuitive meanings. Okay, so this result obviously suggests that we should actually do something to optimize rho, right? So the idea is here simpler what I'm going to analyze, which is actually in some way the algorithm itself existed in the literature in various ways. So not exactly in the same way, but a very similar algorithm. So the algorithm is not novel. But the idea would be here just you design some map so that you optimize rho, right? You can optimize it in many ways, maybe gradient based, maybe in other ways. And use this to prove convergence that is uniform in time, right? Because if you actually use a scheme that minimizes rho, then you can actually have an MSE bound that's uniform in time. So you can have a control over the number of iterations, and you can quantify how fast you get better over iterations. So as I said, similar ideas are considered in the literature. Minimizing the importance of minimizing the variance of the importance sampler is one. There are other divergences. People have done KL minimization. There's a paper on alpha divergence minimization and so on. But interestingly enough, actually nobody took it to the point that you perform an optimization procedure, you go back actually, and then you derive the MSE bound. You actually plug the properties of the optimization actually into the MSE bound, then you get like a full bound of the importance sampler. Right? So that's what I'm going to do. So one thing that eases our job like a lot is if you limit the families of proposals to certain families, in this case, for example, an exponential family. So if you choose Q as an exponential family, a very nice picture emerges is that this rho function that appears in the bound is actually convex with respect to theta, right? So this is one like this was also sort of shown in this paper with Ryu and Stephen Boyd that they show this rho function is actually convex when you choose a proposal from exponential family, and also it is mainly independent of the target as long as the quantity itself is finite, right? So can we actually use this property to define an algorithm and then analyze it straightforwardly because we know that rho is convex? So what I'm going to do is exactly that. So to do that is I'm just going to define like an extra notation where I'm going to define an unnormalized version of rho. So instead of rho, I'm going to use R because as you can see, I can't actually compute rho because rho is originally defined with the pi, original pi. But I can actually compute R and the gradient of R because I can compute big pi, right? So I'm going to always define R and I'm going to always use R as an object to minimize and so on. But obviously minimizing R is going to minimize rho because they are same up to a constant, right? So R is defined this way and gradient of R is actually, it has a nice form. It can be written as an expectation, hence you can compute it by sample. So minimizing R obviously is same as the minimizing rho. So what I'm going to do is simply to define a scheme that minimizes R. And what we can do obviously is very simply just define a stochastic gradient scheme, right? So in this case, I'm going to use projections here. Initially, this was just for theoretical reasons. You can remove the projection and prove the same results. So here for the ease of analysis, it's just a projected scheme. And we are going to basically perform this scheme as an adaptation scheme where GT here is the unbiased gradient of R, which is computed by just sampling, as you can see in equation 3. So one result before I go to the MSE bound is that obviously in optimization literature, this is a very well-studied algorithm. This is one particular result. There are more results in the paper that I'm going to show as a reference. This is one particular result of SGD, for example. Kind of result you can use for analyzing the MSE. But this is, if you are running, so this lemma basically says that if you are running this SGD scheme here, right, and your gradient is unbiased and your gradient variance is finite, this is an assumption here, but actually we have a proof of this in the paper. But for the ease of presentation, this is just an assumption here. And if you choose a particular step size, that is decaying with a square root. So beta over square root, beta is just the scaling. Then you basically have this sort of error bounds in the convex optimization literature, right? This is sort of very, very standard results. One difference to note is that I'm using here an iterate average to prove this result, right? This is not the last iterate of the algorithm, although again, in the paper, we have that result too. But here, for the ease of analysis, I am using theta bar as a parameter of the proposal, or well, I will use it. But before that, just from an optimization perspective, if you were to minimize this R with stochastic gradient scheme, and you wanted to analyze the optimization error, this is the error in function value, an expected error because we have stochastic gradients, you would get this sort of 1/squared of t rate, right? So you have a certain convergence rate to the minima because of the convexity you have in the problem. And of course, a result about R would translate to a result about rho, basically, again, scaling the factors here. Okay, so the idea is we know that this happens if I adapt my proposal by using gradient of R. Can I actually use this in the MSE bound? Which the answer is obviously yes. And what happens is eventually using that convex optimization result actually enables you to get an MSE bound for the optimized importance sampler. So this is very different than what you would have as a generic 1/n result with t dependence in it, because now the t dependence, that's the iteration count, is explicit, right? So you exactly know what happens with iterations. You know uniformly that the error is bounded if you follow this strategy. And you also know what happens asymptotically. For example, here, you can see that this term and this term, they have square root of t, 1 over square root of t rate. So these are actually decaying with a certain rate. And this is never going to decay. So this is never going to go away. This is your asymptotic error rate. And it is characterized by rho star, which is basically the minimum value of rho, which is basically, in this case, the minimum value of your targets, the minimum distance of your target to the exponential family, right? So ultimate quality of your proposal in some sense. So this allows you to tell like a few stories, like saying, okay, what happens asymptotically is asymptotically, we have this error rate for this scheme, right? So this is slightly worse than an IID sampler. You know, like the rate is same, 1 over square root of n, but it gets worsened by like square root of rho star, right? That's the price you pay if you choose an exponential family proposal and your target is actually outside of this family. And if your target is in the exponential family, then you have the optimal rate, right? So it's a very intuitive picture, but you know, that's what emerges from the result. And also, like, this sort of results can be used to some extent understand how parameters interact with each other. For example, in this case, you can play games like this. So beta, remember, was the parameter of the step size of the algorithm, right? So the step size decays, but there's a scaling of beta. And for example, this result allows you to tell stories like if you choose your parameter number of particles inversely proportional to beta, the error simplifies this way. And if you further choose your number of steps inversely proportional to square of beta, then you actually get like a uniform error bound in terms of beta. So what happens here, for example, is that if you want to get more precise error by an order of magnitude, then this tells you, oh, then you have to increase your number of particles by an order of magnitude, and you have to increase your number of iterations by 2 orders of magnitude. So it's a relative, it tells you sort of a relative story of what you need to change and how much you need to change them in order to basically increase your error. And you can control the final error with the beta parameter or a single parameter. Okay, so this was like a very simple result from the paper, and there are like more results about different SGD schemes and different combinations of parameters. And then this implies the asymptotic rate, as I mentioned. And then I will very briefly, because I have, I think, almost maybe 7 or 8 minutes, to the case of proposals that are not exponential family, right? Because exponential family what gave us convexity, which was very good, and it like allowed us to get really nice and intuitive results. But if you have a general proposal, then it's not clear what happens, because then you have to perform actually a global optimization procedure. So here in this case, we can recall our original theorem. So it is the same theorem like I showed in the beginning about the MSC, but it's slightly written in a different way. So instead of writing rho, here I wrote R, and I embedded the normalizing constant into this constant. So it's slightly the same results in a slightly different way. And as I mentioned, if rho is a general proposal, then R is a non-convex function. So can we use actually some results from non-convex optimization literature to actually develop a scheme that optimizes R, and it gives us like a similar error guarantees, at least uniform in the number of iterations. So in order to do this, what I'm going to use here, at least in this talk, is SGLD, stochastic gradient Langevin dynamics, because without going into too much detail again, we know, or there are a lot of results lately in the literature showing that if you implement a Langevin dynamics that follows gradient of R, or gradient of a cost function or potential, then this acts as a global optimizer, or at least provided that your temperature, inverse temperature, is high enough, and then the samples coming from the SGLD will be close enough to minima, right? So you can quantify the difference. So because of this global optimization properties, I am going to just use SGLD as an adaptation scheme rather than SGD as I did in the previous case. So basically, I'm going to design this map that's an adaptation map as an SGLD step. or like a similar scheme. In actually the paper, I'm also using underdamped Langevin dynamics for this, and then quantify the error in the same way. So in this case, there's one detail about the gradient computation, probably not very important, is that the generic gradient expression can be written as like in this way, in this case. We just will do to compute the gradient, we will assume that the proposal in this case is reparameterizable. So what it means is in order to sample from Q, we can actually sample from a distribution that's, let's say, a Gaussian or another distribution that's independent of theta. And we can compute a sample by applying a deterministic transformation to this sample that depends on theta. So only dependence of theta would come through this transformation. And then stochastic gradient could be written this way. And what I'm going to define, sorry, the gradient can be written this way. And what I'm going to define as stochastic gradient is just what appears inside the expectation, right? So this is what I would call stochastic gradient, obviously, provided that epsilon is random, right? So these are the notation that I'm going to use here. In this case, I will consider SGLD as the optimizing like adaptation of the parameter, and H is the stochastic gradient of R. And this is basically what I call as an SGLD scheme, or what's called an SGLD scheme. Eta here, the step size, is the step size, and beta here is the inverse temperature, right? So I don't confuse it with the other beta, because these are two different papers. There's an overlap notation, but this is just a parameter of SGLD. So what I call this scheme is stochastic overdamped Langevin adaptive importance sampler, but it's nothing different than just optimizing R, in this case, with an SGLD rather than SGD. So in this case, what kind of proposal we can account or we can like use in this scheme is a bit problematic to define, because only requirements we need actually for convergence of this scheme is the requirements on the gradients, right? So instead of defining a certain parametric family of proposals, what we assume just is that this gradient of, you can see the expression here, this gradient will satisfy certain conditions, right? So this is not nice in some sense, because these are implicit assumptions and these need to be verified for a chosen parametric family. But this is what I was able to do at the moment. So in order to, at least these assumptions will be the most relaxed assumptions. So you can see, for example, I assume stochastic gradient that's not uniformly Lipschitz in theta, and that's not uniformly in epsilon. So they're like, they are relaxed. They allow for growth in epsilon or growth in theta in both cases. So these are relaxed compared to uniform Lipschitz assumptions. And also, of course, we can't assume now convexity. We don't have convexity, but we have to assume some sort of dissipativity or something that ensures the geometric ergodicity of the underlying Langevin diffusion. So in this case, we will assume a local dissipativity assumption. So again, this is local because we allow growth or change in epsilon here. So we don't assume this uniformly in epsilon. But intuitively, these two assumptions basically imply that we have Lipschitz gradients of R, and dissipativity is also satisfied for R. So a Langevin diffusion that if you would run with using the gradient of R, that would be geometrically ergodic, right? That's what it says. So for under these conditions, we have the similar optimization results as the SGD. Obviously, the bound itself is very different, but we have this quantity bounded. So this is the iterate of the SGLD evaluated at whatever potential it's optimizing. In this case, it's R, the distance to R star. You usually have this sort of bounds, right? So there is three terms. So the first term is basically coming from the fact that Langevin diffusion is exponentially converging to its stationary measure. So this is going to decrease exponentially fast with respect to iterations. This is basically coming from the discretization error of the Langevin diffusion. Again, without going to details, this is just the order of step size of this, 1/4 of the step size of the scheme you use. In this case, it's SGLD. And the last term is basically the gap comes from the fact that you're using the last sample of SGLD as an estimate of the minimum, but obviously the sample will deviate from the minimum to some extent And this is quantified by C3. And of course, obviously, intuitively, C3 decays as your inverse temperature increases. Again, that's just because the distribution would concentrate around minimum. And as a final result, you can simply take this sort of result and plug it in the adaptive importance sampling estimate, or the bound, the MSE bound, because now we show that we can optimize R, we can use this result to show that we optimize rho as well, and then we actually obtain sort of a uniform bound. And this is again like a similar quantity. The first term will actually decay over time. So if you take supremum over K, this is going to disappear. So you have like a finite time. Sorry, you have a result that's basically uniform in time, right? So that we know that this does not blow up over time. So basically, to wrap up everything, basically this what I did. I proposed or reproposed stochastic gradient-based methods to choose optimal proposal, and the point was more like the build scheme so that they are amenable to analysis. So that's and for exponential family proposal, basically the problem was convex. And some details like we assumed finite gradient variance, that's not necessary, that's actually proved in the paper rather than being an assumption. Also, like I showed an iterate average SGD, I used the average iterates for an estimate of an optimizer, but that's not necessary. You can use the last iterate convergence, so the algorithm doesn't need to store anything. And we just, like in this case, the results were all non-asymptotic. They were decaying in time, so time dependence was explicit, and the error was uniform, right? And also for the non-convex case, it's the same story. Instead of using a SGD, we use stochastic gradient MCMC methods as global optimizers, right, not as samplers. So in this talk, I just showed the results regarding SGLD, but the paper also includes, underdamped Langevin MCMC as an alternative optimizer. And similarly, the results were the same nature, that non-asymptotic and uniform in the number of iterations. So there is a challenge to overcome. Obviously, the more popular schemes using population-based methods rather than like this, parameter optimization schemes. Obviously, one needs to show that those schemes, the mixture proposals and so on, they actually optimize chi-square divergence, which is kind of difficult because they form an interacting particle system, and it's not straightforward as in the parametric case that you basically minimize the cost function. Thank you, and that's all. Thank you from me. And these are the references.
Thanks very much, Deniz. I'm just going to stop recording and then open for questions.